and welcome to another WJEC A level physics question. This time it's question 1 from June 2018's Unit 4 paper, and it's about capacitors. For the first part of the question, we've got a parallel plate capacitor that's been made up of two square aluminium plates with sides of length 18 centimeters. The capacitance is 2 nanofarads, and we've got to work out the separation of the plates. So we can use the parallel plate formula, C equals epsilon naught A over D. D therefore is epsilon naught A over C. So put in some figures. Epsilon naught is in the data book, 8.85 times 10 to the minus 12. The area will be 18 centimeters, so turn that to meters squared because they are square plates. And the capacitance was 2 nanofarads. Don't forget the nano is 10 to the minus 9. That will give us 1.43 times 10 to the minus 4 meters, or about 0.143 millimeters. Next, we've got to find the capacitance of the combination shown below. The first step is to remember that capacitors in parallel add up. So the parallel section is simply going to be 4 nanofarads. Next, to find the total capacitance, we add reciprocals. So we have 1 over 4 for the parallel combination, 1 over 6 for the capacitor that's in series. Lowest common denominator is 12. So we have 3 over 12 for a quarter and 2 over 12 for a sixth, which is 5 over 12. And then the total capacitance will be 12 over 5, or 2.4 nanofarads. For part 3, we've got to show that the charge stored on a 2 nanofarad capacitor in the following circuit is 18 nanocoulombs. Well, remember that the first thing we did on the last part of the question is we simplified these two in parallel to a 4 nanofarad capacitor. Then, effectively, what we've got is a series circuit where we've got a 15 volt supply with a 4 nanofarad in series with a 6 nanofarad. And capacitors in series have the same charge. Now our capacitor formula is C equals Q over V, and if we rearrange that, we got V equals Q over C, and this shows us that the PD across a capacitor is inversely proportional to its capacitance. So in this circuit we've got a 4 nanofarad and a 6 nanofarad capacitor, so we've got effectively 10 shares of the voltage. So the PD across the 2 nanofarad capacitor combination is going to be 6/10 of the 15 volts. So remember, it's the inverse proportion between V and C. The 4 nanofarad capacitor gets 6 shares, the 6 nanofarad capacitor gets 4 shares. So that will give us a PD across the 2 nanofarad capacitor combination of 9 volts. And then finally we can say that the charge stored on any of those 2 nanofarad capacitors is CV. So 2 times 10 to the minus 9 times 9, which is 18 times 10 to the minus 9, sorry, I wrote 19, 18 times 10 to the minus 9, or 18 nanocoulombs. Quick point here, remember that the two capacitors that are in parallel, things in parallel, have the same PD across them. So if there's 9 volts across the combination, there's 9 volts across each individual capacitor. Next, we've got to calculate the total energy stored by the capacitor combination. So I'm going to use U equals a half CV squared, remembering that the combination had a total capacitance of 2.4 nanofarads, and the PD across it is 15 volts. Putting that into a calculator, we end up with 270 nanojoules. Or if you prefer, 2.7 times 10 to the minus 7 joules. Next, a group of students investigated the charging of a capacitor through a resistor and obtained the following data. And we got graphs of the potential difference across the capacitor against time and the current flowing in the circuit against time. Now this is a charging circuit. So we've got to draw a circuit diagram of the apparatus that might have been used to obtain the data. So we're going to have ourselves a power supply. We're going to have the capacitor, and we're going to need the resistor to be in series with a capacitor so that it doesn't effectively instantly fully charge up to the total of 12 volts we can see on the diagram. We're going to need an ammeter in the circuit to measure the current, and we're going to need a voltmeter connected across the capacitor. Maybe we could add a switch or something, but that'll be fine. Next, we've got to use the graphs to determine the EMF of the power supply, the resistance of the resistor, and the capacitance of the capacitor. Well, eventually the capacitor will reach its maximum PD of 12 volts when it's fully charged, and when it's fully charged, the PD across the capacitor will be the same as the PD across the cell. There'll be no current flowing when the capacitor is fully charged, so the PD across the resistor, V equals IR, will be 0. So the PD across the capacitor is the same as the PD across the cell, which is the EMF of the cell. So simply we can state that the EMF is 12 volts. To find the resistance of the resistor, we can use V over I. And if we take T equals 0, at T equals 0, the current flowing in the circuit is about 2.7 milliamps. At T equals 0, the PD across the capacitor is 0 volts, so therefore the PD across the resistor is 12 volts. Remember, these two PDs must add up to 12 volts. So we got 12 volts over 2.7, I think it was milliamps, let me just double check that, 2.7 milliamps, and that will give us 4,444.4 recurring, so let's just call it about 4.4 kilo ohms. I'm going to use that answer in my next calculation, so I'm going to store it in a memory there. There's a few ways of doing the last part of the question. A fairly straightforward way would be to write an exponential decay equation for the current. You could write an exponential charge in equation for the PD, but the decay equation is a little bit simpler. So for the current, we can write I equals I naught e to the minus t over RC. All we need to do now is choose a value for time and the corresponding current. So let's use 10 seconds where the current seems to be near enough 0.8 milliamps. So we've got 0.8 milliamps is equal to 2.7 milliamps. I'm not going to put the millis in, they will cancel. E to the minus t over 4.4 times 10 to the 3 times C. So I'm going to show the steps of working. You can do it in one step if you're really confident, but let's do this in bits. So the first thing I'll do is divide both sides by 2.7 and take logs, and that will give me, the time by the way was 10 seconds, that will give me minus 10 over 4.4 times 10 to the 3 C. A little bit of rearranging, C will be minus 10 over 4.4 times 10 to the 3 times that log of 0.8 over 2.7. Basically the C and the log function have swapped places. We put those figures into the calculator, we come up with an answer of about 1.8 millifarads. I wouldn't go to any more than two significant figures here personally because of the inaccuracies of reading from that graph, where that's probably just very slightly under 0.8 milliamps. So thank you very much for listening. Please remember to like and subscribe, and feel free to leave any comments. Goodbye.